Okay, let's set the scene. You've done everything right. I mean, you've provisioned the absolute best hardware money can buy, and yet your application is just grinding to a halt. It has to be one of the most frustrating things a developer can face, right? So today we're going to put on our detective hats and solve this modern mystery.
I mean, just look at this setup. We're talking 32 cores, all roaring to go. A massive 128 gigs of RAM just sitting there, waiting to handle literally anything you can throw at it. Your infrastructure is a fortress, right? Built on a brand new, lightning-fast server cluster. On paper, this thing should be absolutely unstoppable.
But it's not. Users are complaining about lag. Page loads are taking seconds, not milliseconds. Your dashboard is just a sea of red, and every single request feels like it's moving through mud. It makes absolutely no sense. The hardware is a beast, so what gives?
So, if throwing more hardware at the problem isn't working, we're clearly looking in the wrong place. The real answer isn't in the machine. It's got to be somewhere deeper, inside the actual logic that it's running.
And this is what we call the high-spec slowdown paradox. Yeah, it's that totally baffling scenario where you have this top-tier hardware, but it's delivering bottom-tier performance. It's a crystal-clear sign that the real bottleneck isn't a lack of power, but something much more subtle.
So the crucial point here is this. We have to stop blaming the usual suspects. It's almost never the CPU, the RAM, or the network that's really at fault. The real culprits, they're hidden in plain sight, inside our code, our database queries, and the very architecture of our services. These are the silent performance killers.
All right, so time for the real investigation. Let's unmask these bottlenecks and take a look beyond the machine.
Okay, here are our prime suspects. First up, we've got chatty communication, like the infamous N+1 query, where just one request ends up triggering a whole flood of others. Then there's blocking I/O. This is the root cause of so many problems because it leaves our powerful CPU just sitting there, twiddling its thumbs. Third, we have missing or just plain bad caching, which forces the system to do expensive work over and over and over again. And finally, an inefficient architecture that's just creating unnecessary friction and delays between services.
Let's just zero in on that fundamental concept for a second. I/O-bound tasks. A task is I/O-bound if it's spending most of its time just waiting for a network call to another service, waiting for a disk read, or waiting for a database query to finish up. And during all that wait time, your expensive multi-core CPU is doing absolutely nothing. It's like having a world-class sprinter who's forced to wait for the bus. All that idle time is the real enemy of performance.
Okay, let's talk about our first and maybe the most common culprit, the N+1 query. Now this one is particularly sneaky. Why? Because the code often looks totally clean and logical, but under the hood, it's unleashing an absolute storm of database requests.
So what is the N+1 problem exactly? Well, imagine you want to show a list of blog posts and their authors. Your code first fetches, let's say, 100 posts. That's one query. Simple enough. But then, as it loops through each of those posts to get the author's name, it makes a brand new query for each and every author. So you end up with one query for the posts, plus n, in this case 100, extra queries for the authors.
And this right here illustrates the crime in progress. Step 1, a single query to grab our 100 posts. Okay. Step 2, the application kicks off a loop. And then, step 3, inside that loop, it executes that author query again and again and again, 100 separate times. Each one of those is a full round trip to the database.
The grand total? A staggering 101 queries, just to do something that should have been incredibly simple. This is the classic N+1 pattern. And believe me, it's a huge reason why so many list pages and applications just suddenly become slow as the data starts to grow.
Thankfully, the solution is just as classic. It's called eager loading. So instead of being lazy and fetching related data one by one, we tell our framework to be proactive. We instruct it to load all the posts and all their associated authors right up front, usually with just one or two highly optimized queries. And what's the result? Well, we go from 101 queries all the way down to just 2. Yeah, 2. One to get the posts and one to get all the authors we need in a single batch. The application then just stitches the data together in memory. I mean, the difference in efficiency is literally night and day.
Let's just look at the numbers, because they are honestly astonishing. The N+1 approach takes over a full second. We're talking 1010 milliseconds. With eager loading, a mere 20 milliseconds. That is over 50 times faster. This isn't just some minor optimization. It is a complete game changer for your application's performance and scalability.
All right, let's move on to our next critical performance tool, caching. Think of it like this. If your database is the huge long-term library, caching is the stack of books you keep right on your desk. It's your application's super-fast, short-term memory.
Now, this diagram shows a really brilliant pattern for protecting your system. A microservice needs some data, right? Let's say a user's profile or some product information. But instead of hammering the database every single time, it first checks a shared cache cluster. If the data is there, bam, it gets an instant response. This simple little intercept shields the database from tons of repetitive queries, and it really quiets down all that noisy chatter between your services.
So when you go to implement a cache, you'll often be choosing between two heavyweights, Redis and memcached. This table kind of breaks down the difference. Memcached is pure, simple, and incredibly fast for basic key value storage. That's its thing. Redis, on the other hand, is more of a Swiss Army knife. It supports complex data structures like lists and sets. It offers data persistence, so you don't lose everything on a restart, and it has built-in clustering. Really, the right choice depends entirely on what you're trying to do.
Okay, so we've identified the culprits. Now let's build your detective's toolkit so you can go hunt them down in your own system.
All right, here is your action plan. First off, audit your highest traffic pages. That's where any optimization is going to have the biggest impact. Next, in development, always enable query logging, so problems like N+1 literally have nowhere to hide. You should also systematically optimize your queries with proper indexing to make your database faster. Then, implement smart caching for data that gets read a lot but rarely changes. Use asynchronous communication to stop services from blocking each other. And finally, profile your application so you know for sure if you're I/O bound or if you're truly CPU bound. And all of this brings us to the most crucial takeaway, really. This isn't just about hardware. It's about a fundamental shift in how we think about performance. This quote really says it all. You know, those small, logical decisions we make in our code, like choosing eager loading instead of lazy loading, that's what determines whether our application can handle 10 users or 10 million. True scalability is born from efficient software design, not just from throwing powerful hardware at the problem.
So let's completely reframe the question. The default reaction to slowness can't be, do we need a bigger server? The first, second, and third question should always be, where is the bottleneck? See, performance is a hunt for inefficiencies. It's not just a purchase order for more RAM.
And that leaves us with one final question for you to take back to your own projects. Now that you've got the tools and the right mindset, what's the hidden bottleneck that's hiding in your system? Go on, go solve the mystery.